Question 12 looks like a special role question. So Gianna's an observer on spacecraft A, watching spacecraft B fly past at a relative speed of 0.51 c. She measures the length of spacecraft B from her frame of reference to be 103.22 meters. Calculate the Lorentz factor. Okay, so the Lorentz factor is just a function of the relative velocity. So we have that, so we can just write gamma equals 1 over the square root of 1 minus 0.51 c. So when we divide it by c, we're going to get 0.51 squared. And we just plug that into the calculator. So that's, let me do it here. So that's 1 minus 0.51 squared is that. And then we want that to the power of negative 0.5. So that's a Lorentz factor of 1.163. It doesn't say how many decimal places, does it? No. Yeah, I know 4 will do. You can't use that chemistry rule of 2 sig figs here. Means you should make this 2 sig figs, or else you get a lot of inaccuracy in your Lorentz factors. It makes a big difference with Lorentz factors. Okay. What's the length of the spacecraft B, according to Gianna, if she was standing in it? Such a strange way of putting it. What's the length of spacecraft B, according to someone on spacecraft B? So we know that L observed equals L naught over gamma. So we just have to say who, this measurement that Gianna took originally, is that L naught or is that L dash? Well, she's measuring spacecraft B from spacecraft A. She's moving relative to spacecraft B, so she's measuring L dash. So this is 103.22 meters equals L naught, like the proper length, divided by 1.163. And so we get L naught equals times 103.22, 120 meters. So yeah, there's no way to round that without. So we get that. So I'm just going to have another go at part C. I didn't really like this question very much, but we'll try and give it a fair go. Gianna's flight instruments record the spacecraft B to take 674.6 nanoseconds to travel past her spacecraft. So what I really don't like about this question is, what the hell do you mean by to travel past her spacecraft? So do you mean you're looking straight out in that direction and the nose passes you and then the tail passes you of the rocket? Or are you saying that the nose makes contact with the front of your spacecraft and then makes contact with the back? What do we mean by 674.6 nanoseconds to travel past? So that's the first clue that this is not going to be something that we're really going to be doing calculations on. It's like not very well defined. State whether a scientist in spacecraft B records a lesser, equal, or greater time for spacecraft A to travel past it. So, and then it says calculations not required, justify your answer. Okay. So if we had a really good sense of what is the thing that we're measuring here, what has spacecraft B actually measured? And then we were being asked, okay, for those same events, what's the time duration that spacecraft B is between them? Then we'd be using some sort of time dilation here, okay? And that would be sort of a real special role question. This one here is more, I would say, a trick of language, okay? So it says, spacecraft B says that, sorry, spacecraft A, Gianna, says that spacecraft B takes this amount of time to travel past her. Then we're asked spacecraft B, how long do they say spacecraft Gianna takes to go past them? And given that these guys are going at the same speed in Well, it doesn't even say identical spacecraft, but let's say for the sake of argument, it is identical spacecraft. Is that even the case? Oh, what a mess of a question. No. Uh, what a joke. Okay, let's assume they're the same length, these two spacecrafts. They're going, both of them consider themselves to be a inertial observer, and the other one to be going past at 0.51c. And what this question is trying to get at is that, well, if one of them, if they're both traveling at 0.51c, and they both consider themselves to be stationary, the other one to be going past 0.51c, then if one of them says, you took 674.6 nanoseconds to go past me, then the other one's going to say, no, 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 you took 674.6 nanoseconds to go past me. Um, only true if their spacecrafts are actually the same length, though, and this question doesn't go to the trouble of saying so. I don't know what to do about that. That's, I wouldn't really, I would probably say, that what the solutions are looking for here is for you to say that it records the same amount of time, and it's because they're both symmetric observers. But I would be I think you would be completely within your rights to say, well, okay, Gianna is the inertial observer of whatever the process this was. She's saying it took 674.6 nanoseconds. She was standing there looking, and it took 674 nanoseconds to go past her. The events that define that that time were defined by Gianna wherever she is, so she's the proper observer. And then to do the time dilation on that, I wouldn't blame you if that's what you did. I don't think this is a very well phrased question. You're actually going to find this quite a lot with special rel, with both special rel and the examination methods part of the trial exam. The people who write them, they just don't have a big bank of hundreds of VCAA questions to look at for them to copy, so they don't do quite as good a job with them. But this is, I don't know, this is particularly kind of lazy in its wording, unfortunately. But yeah, the answer they're looking for here are that it's equal time, but I wouldn't take it too seriously if you didn't get that. I didn't quite understand what they were getting at there. Okay. Rocket past there. If you get, you won't from the VCAA, but if you get a question that feels a little bit ambiguous like this, like what do you mean travels past her, then draw a picture and make it clear to the examiner what you are interpreting this question to mean, right? And then if they have some other interpretation of it, but you feel like your interpretation was correct, then you can tell me and leave it to me to argue with the VCAA for months. But it's not going to happen. But like there's no harm at all in making your assumptions explicit. So Jan is the proper observer. This means that spaceship B will measure a dilated amount of time, so a larger amount of time. All right, question 13 looks like it might be about standing waves. In a class experiment, a group of students investigated the speed of a wave in a rope. One of the students oscillated one end of the rope at right angles to the length of the rope, so transverse. The other end of the rope was fixed to the wall. The resulting pattern is shown in figure 13. The student's hand is oscillating at 1.5 hertz, so we know that the frequency is 1.5 hertz. And the length of the rope is 1.2 meters. So the temptation here might be to say, oh, the wavelength is 1.2 meters, but it doesn't look like a perfect one wave fitting in that rope there. So let's just put that aside for a minute, and let's just say L equals 1.2 meters. Determine the speed of the wave in the rope. Okay, so if we want to know the speed of a wave, sort of our go-to equation is V equals F lambda. So if we knew lambda, we'd be set. We've already got F. We could find V from V equals F lambda. But we need to find lambda here. And so the way we do that is we look at this and we can see that this looks like a harmonic of a half open, half closed system, right? So we've got a node at one end and an antinode at the other. And so because it's a half open half-closed system, we're looking at quarter waves lengths. So we got 1/4, 3/4, 5/4. Okay, so our wavelength is 4/5 of, sorry, our wavelength is 4/5 of the length of that pipe, because we've got 5/4 waves in this full length. So that's 4/5 of 1.2 meters is 0.96 meters, which, sorry, I just did the calculation off screen, but you can take my word for that. So now we can stick those two together. We've got a frequency of 0.96 meters. Frequency of 1.5 hertz, a wavelength of 0.96. So we're going to have V equals 1.5 hertz times 0.96 meters equals 1.44 meters per second. Okay, so that's our wave speed. In question 2, they ask us to consider the same piece of rope. We're doing the same thing with it, but we're just going to oscillate it at a different frequency, and we're going to get a different pattern here. And this looks like, instead of having the sort of the 5/4 pattern, we've now got the 1/4 pattern. Okay, so we've got something that has a wavelength which is 5 times longer. Okay, explain how the pattern in figure 14 is related to the pattern in figure 13. Okay, so I'd probably start just by saying both are standing waves due to harmonic frequencies. So just make it clear that you know that these are standing waves and they're harmonics, which sort of makes the rest of your answer easier, because now you can just talk about the differences between them. Okay, so explain how the pattern is related to the pattern. So you probably want to say, what's the difference in frequencies? So lambda in figure 13 we found was 0.96 meters. Lambda in figure 14 is going to be, well, if 1/4 of a wavelength fits in the length of the rope, then that means the wavelength is going to have to be 4 times the length of that rope. So it's going to be 4.8 meters, i.e. Figure 14 has a wavelength 5 times longer than figure 13. F13 is the 5th harmonic, while F14 is the fundamental. I know that's the fundamental. Figure 14 is the fundamental, because we couldn't get a wavelength even longer and still have a node here and an antinode here, because there'd be no way to have a peak or a trough at the end here with a 0 at the start here with a longer wave. Okay, so that must be the longest possible wavelength. So you could say it has a wavelength 5 times longer, or you could say a frequency 5 times higher. 5 times lower. Or you could phrase those in reverse direction or whatever it might be. But yeah, you want to make it clear that you know that this is the fundamental and that this is a higher harmonic, and specifically in this case, the fifth harmonic. Note, just this isn't part of the question, but just generally, for these odd uneven situations, there's no second or fourth harmonic. So the harmonics for this is that's the fundamental. The next one is that, and then the one that we've got is the 5th. So that's n equals 1, n equals 3, n equals 5. For these odd ones, there's no n equals 2 because if you doubled the frequency here or half the wavelength, then you would actually have a node at the end here, and we don't have a node at the end here. So so we only have odd harmonics here. Okay, question 14. A group of students set up a sound generator and program and produce a sound at constant intensity, single frequency. The sound is directed towards a double slit arrangement where it passes through slits 1 and S2. So we're doing Young's double slit, but we're doing it with sound. Students record positions MA, MB, MC, where successive minima in intensity occur along the screen to the right of the double slit. Okay. I would say that's to the left, but anyway. Point P is directly across from the center of the two slits. This is shown in figure 15. Okay. Students record the following distances: 3.62 meters, 3.43, 3.3. Okay, so these distances are from the sources themselves to the points. So we're not talking about distances along this wall here. We're talking about distances to the points. Okay, determine the wavelength of the sound generated. Show your working. Okay, so if these are successive minima, that means there's no minima in between them, then that means that they are integer wavelengths apart in terms of path difference. Maybe that's a little bit hard to talk about, but we know that nodes occur at path difference equals n plus a half lambda. So a half integer multiples of the wavelength. Okay, so M, A, M, B, and M, C are just consecutive values of n here. So they might be like 3.5, 4.5, and 5.5. Okay, so what we want to do here is we want to find these path differences and see how they're changing for as we go from C, which is the closest, to B to A. Okay, so delta L for C is 3.35 meters to source 1 and 3.95, so 0.60 meters. Delta L at B, which is a bit further away, so we're expecting a bigger path difference, is 3.43 versus 4.43. So that's 1 meter. And delta L at A is 3.62 versus 5.02, so 1.40 meters. Okay, so we can see that as we go from one to the next, the difference is 40 centimeters, i.e. as we go from 1.5 multiples of lambda to 2.5 multiples of lambda, the difference is 40 centimeters, so lambda must be 40 centimeters. So I could add in a line here that says, therefore, MA and MB it's hard to phrase this. Their path differences will be different by lambda. Okay, because the difference between 1.5 lambda and 2.5 lambda is lambda. So if the path difference of one is 60 and the next one's 1 meter, then you know that the wavelength must be 40 centimeters. Okay. Two of the students, Melinda and Chan, are discussing how changes to the sound may affect the positions and qualities of the points MA, MB, and MC. Melinda suggests that a higher frequency, so shorter wavelength, will cause the positions of the minima to shift further away from point P. Chen suggests that higher frequency will cause the distances between the minima to decrease. State whether each student is correct or incorrect. Justify your answers. Okay, So putting a higher frequency in is going to shorten the wavelength, which means you're going to shorten the distances between nodes. You're going to create a sort of a denser pattern of nodes and antinodes. So you could sketch that out generally, and you could make your case in broad terms in that way. But probably a more effective system is to say, by analogy to Young's double slit, using light, we know that the fringe separation will be, and because we're using an analogy here, let's call it an approximate. It really is an approximate anyway. So is going to be lambda L on D. Right. So this is just one way of answering this question. There are quite a few different ways. If you want to read me your answer, I'm happy to say. Oh, obviously, I'll be marking this anyway. So, but yeah. So if you're unsure whether your answer is right, maybe just wait. But lambda L and D, therefore, increasing frequency, which is reducing the wavelength, reduces fringe separation. So quiet points, nodes are closer together, as will, of course, will be the antinodes. Close together, right? So, and then on all these questions where there's this argument between people, it's pretty standard question type. You got to really explicitly say who's right. Okay, so Chen's saying that the distance between the minima is going to decrease. So Chen is right. Chen is correct. Okay. The key things that you want to capture in your answer are, if the wavelength decreases, then the distance between minima decreases. Therefore, Chen is correct. Okay. Oh, we're getting photoelectric effect, so we must be close to the end. In stage 1 of an experiment, green light of frequency 5.5 times 10 to the 14 hertz. Is shone onto a metal cathode. The ammeter displays a reading when the DC voltage source is 0 volts. Yep. So we've got no back voltage at all. So we're just measuring pure photoelectric effect at this point, and we get some sort of current. And then the ammeter reader drops to 0 when the DC voltage is increased to 2.03 volts. So the stopping voltage here is 2.03 volts. Okay. Explain why the ammeter registers a reading when the green light is shone onto the metal cathode, and why the reading drops to 0 when the DC voltage is increased to 2.03 volts. Okay, so there's two things to explain here. Why do we get current when we shine green light on the metal? And then why does it drop to 0 when the DC voltage is 2.03? And it's only worth 3 marks. So we don't want to say everything we know about the photoelectric effect here. We just want to say, why do we get a current? And why does it drop to 0? So let's answer those separately. All right, why do we get a current? The photons in the light give their energy to electrons, which then have enough energy to escape their metal. And they've called it a metal cathode. So let's reflect that language back to them. To escape the metal cathode, and are collected by the anode and registered in the ammeter. Okay, so that's why you get a current. And then you want to say, why did it drop to 0 when the DC voltage is increased to 2.03 volts? So what we want to say here is each photon only has a limited amount of energy. So that means each electron only comes out with a limited amount of energy, which means there's a limit to how much work those electrons can do against a back voltage. Okay, so however you want to structure that answer, I'll write down my version of it in a minute, but that's what we're basically getting at here. Each photon only has, why not just work it out? Because you're probably going to need to in the next few questions anyway. So why not just work out how much energy this photon has? It's going to be H times F. We want it in electron volts because we're going to compare it to this voltage thing here, right? So let's work that out. 4.14 times 5.5. So we've got a 10 to the negative 14 and a 10 to the 14 here. But I know that when I work with visible light, I get nice integerish type amounts of electron volts. So I'm just going to go straight ahead and say it's so it only has 2.277 electron volts of energy. Right, so we can work out how much energy each photon has. This means electrons emerge with at most this energy minus the metal's work function. I'm going to run out of room on my page here, so maybe I'll just say it out loud to you. Therefore, a back voltage above whatever that value is will be able to stop them. Okay, so the key points you want to point out here are why do we register a reading at all? Well, it's because photons are coming in, they're giving energy to electrons, that's letting them escape the metal, and so they're being detected in the circuit. Why do they stop? Well, because they don't have infinite amounts of energy. They have a certain fixed amount of energy, therefore the electron has some fixed amount of energy less than that, which means some back voltage will be able to stop them. Okay, they would have to do work. You might want to mention that in order to cross the voltage, they have to do work. I would probably recommend using the word work. Okay. Yeah, let's finish off this answer. To cross a 2.3 volt field, they must do 2.3 electron volts of work. I.e., if they don't have E greater than 2.3 electron volts, they can't make it. Something along those lines. That looks like it was a really long answer for mine, but I'm writing in a much smaller space than you. So that would be about, maybe about, I tend to think if something's worth 3 marks, you probably want to put about 4 dot points, roughly speaking. Okay, determine the work function of the metal. Okay, so because we've already worked out, so we know that the maximum kinetic energy of electrons is going to be equal to how much energy the light gave them minus the work function of the metal. Okay. Now, we also know that because the biggest field that they could cross was 2.03 volts, sorry, 2.03 volts. 2.03 volts. Before they stopped, that means this guy here must be 2.03 electron volts, is the most amount of energy that any of them have. We already worked out previously that our HF was, where did I do it? Oh, I've got rid of it. What an idiot. 5.5 times 4.14, 2.277 electron volts was how much energy our green light has, minus phi. So phi in this case is, the work function is 0.23 electron volts. 237? Yeah, 237 electron volts. Yeah. Which, to be honest, is absurdly small. I'm a little bit perplexed by that. I don't think any real metals have work functions that small. So let me just quickly think that through in my head. Green light is about 2 electron volts, right, for that? Yeah. Okay. All right. I mean, this question is just, they're using some weird exotic metal that has a very, very low work function. So it's, I mean, this metal, if it were just sitting around in your house, would be constantly sparking off electrons. So so probably not a super stable metal. Anyway, all right. Okay, now we're going to stage 3. Stage 2. The stage 2, the experiment is repeated using violet light of twice the intensity. So both violet, so it's higher frequency, and also more intensity, so more photons. Compare and contrast the 2 stages of the experiment in terms of any reading observed on the ammeter display when the DC voltage is 0 volts. Okay, so part I, twice intensity implies more photons. 2 times more photons implies more electrons released. Implies higher current. So assuming that the electrons can be released at all, we would expect to see more of them with higher intensity than with lower intensity. You may want to say, since F green was greater than threshold, so will F violet be. I.e., there's not some problem here where, because we've dropped the wavelength, we might no longer be releasing any. We're using higher frequency. So if anything, we're going to be getting even more electrons coming out, okay? Because they've got more energy, so you can sort of get electrons from even deeper inside the material. You don't have to talk about that stuff, though. We're doubling the intensity, so we're doubling the number of electrons that are coming out, roughly speaking. To get around that subtlety, you just say more electrons, and just don't worry about quantifying it. Okay, 2. Okay, any reading observed on the ammeter display when the DC voltage source is increased to 2.03 volts. So the current will no longer be 0. So what you want to say here is violet photons have more E than green. Therefore, photoelectrons more energetic. Therefore, some photoelectrons will have kinetic energy greater than 2.03 electron volts. Okay, and then maybe say, therefore, they will be able to cross. To do enough work to reach the anode. Okay, So we've got more energetic electrons, which means in order to stop them, we would need a bigger back voltage. So 2.03 volts is no longer going to do the job. Okay. Um, you might be tempted to try and work out exactly how much current there would be. It's a fool's game. You'd have to know all about the details of the chemistry of the metal. So you just say there's some current. Who knows how much? If you wanted to, you could accompany these guys with some nice little graphs. Certainly wouldn't hurt. So at 0, might as well use the colors. Here's my green graph. Here's, I don't know the purple one. I'll use grey for purple. Here's my purple graph. So we can see that at negative 2.03, we've still got some current on the purple graph. And we can also see that when there's 0 voltage, we've got twice as much current or way more current on the purple line. Okay. Don't know why I've made it so small in here. Probably could have drawn it here properly. Okay. All right, part D. Explain the effect that doubling the intensity of light would have on the experimental results according to the wave model. Indicate whether the model's prediction agrees or disagrees. Okay, this is a pretty simple version of this type of question. Every exam you do, just about, will ask some version of this question. So it'll say, here's something that the wave model predicts, or here's something that the particle model predicts. Is it right? Is it wrong? Or it might ask you to list the things that it gets right and wrong. There's a million permutations of this question, but they all just come down to how well conceptually do you understand what the photoelectric effect is telling us. Okay, so let's dive into an answer here, but we want to tailor our general answer about the photoelectric effect to just this specific situation. So explain the effect that doubling the intensity of light would have on the experimental results if the wave model were true. So if the wave model was true, doubling intensity would mean much stronger electric field oscillations. Okay, so doubling the intensity would create stronger electric field oscillations. This would create photoelectrons with more energy. So remember, so intensity or brightness of light in the wave model is about the amplitude of the electromagnetic wave. So if we've got big electric field oscillations, then we'd expect to be pushing those electrons around harder, giving them more energy, making them vibrate faster. So more energetic electrons. Okay. So you want to say, you want to build your answer here from what is the wave model? What does it actually say? To what predictions does it make about this experiment? And then lastly, whether those predictions are correct. Okay, so we've said that the wave model, so this would predict more electrons escaping, which would be higher current, and more energetic electrons, higher voltage required to stop them. Yeah, you could probably just say higher stopping voltage there if you wanted to, but I'm being really explicit. Okay, so we've got sort of model explanation. So relevant details of the model talked about. Then we've got specific prediction. Now, what I'm going to do, just so that I can refer to them in a non-confusing way later, is I'm just going to call these two predictions 1 and 2, right? And if you've got multiple predictions, label them so that you can call them later. And then lastly, you want to say whether it gets it right or wrong. So the wave model correctly predicts 1, but 2 is incorrect. Okay, and then so actual results. And that's a pretty good structure for for most explained questions when you're being asked about an experiment, to be honest, is, and even like writing a hypothesis for an experiment or something, is to say, okay, or an abstract for your experiment, okay, here's our model. It says this stuff. Therefore, when we go into a specific scenario and actually test this, here's what we're expecting to see. And here's what we did see. Was it right or was it wrong? So the only thing that would change if we were being asked about a particle model now is, well, the details of what we're explaining would change. The predictions that it makes would be different. And the results would obviously say it's right. But beyond that, the structure is actually the same. Okay. So it doesn't matter what question you're answering, this structure is going to be a useful one.